Oh, over here. Okay, we are on page 67. So far we have done types of solubility math problems. We've done given solubility. And remember, what is solubility? The maximum amount of solute that can be dissolved in a given volume. So the unit is moles per liter. So given the molarity of a saturated solution, find the KSP. We did that one yesterday and the day before, yes? And you practiced that for homework, hopefully. We have, in the past, we have done titrations. I'm not going to list those, though, because we're going to go over it again, okay? We did, will a precipitate form when we mix two solutions? And given solubility, find KSP. Is that a mix and match or is that a dump and stir? So you will be given the molarity of a saturated solution. Are you dumping something in and stirring it until you can't dissolve anymore, or are you mixing and matching two things and forming a precipitate? You are dumping and stirring, because that's how you get a saturated solution of, and that's, like, it's the most straightforward way to get a saturated solution, yes? And if you're finding the solubility, you're just finding the molarity of that saturated solution. So that's, yeah. So this is dump and stir. Dump and stir. So that means your ion concentrations will be proportional. Proportional to the coefficients in the SEE. Will a precipitate form when you mix two solutions? Is that dump and stir or mix and match? That is mix and match. So will the ion concentrations be proportional to the coefficients? No. What tools do we use for type 1, given solubility, find KSP? What are the two main tools? We use the C, and we use the KSP. What tools do we use when we're looking at will a precipitate form? So we're thinking of those questions like we did yesterday. Yeah. So once again, we're going to have the C. We're going to have to use Q. If we're mixing two solutions, we're going to have to do some, what kind of calculations? Dilution calculations. And I guess I should have called this B, and then C, and then D. I'm like, I don't know. Or should I just call it 0 for the first one? I don't know. Okay, let's call that A, B, and C, and let's call this 0. Predict the precipitate. Okie dokie. And today, we are going to go backwards from type 1. Instead of being given the solubility and finding the KSP, we are going to, given the KSP, find the solubility. We good? Okay. So we want to find the solubility. What is solubility? What is solubility? In this case, we're going to use the slightly less fancy definition. It is the concentration of what? A saturated solution. Okay, so if you've got A2B in equilibrium with 2A plus B 2 minus, and if we let the solubility equal X, what does that tell us about the concentration of A2B? What does that mean about the concentration of A2B if the solubility equals X? Huh? Bracket X, yes. Okay, X molar. All right, and you wouldn't have to put it in brackets here because you're just saying that's its concentration. So up here, you would say that this is X molar. Yes. Then what would the concentration of A? It would be 2X, and B would be X. All right, and that's really all you need to do to solve these problems. You have to have that let statement. You need to have the C. You need to show the ion concentrations. Yeah, you could write this as a rice table if you prefer, but you can just do it in one line. So if you wanted to do this, okay, so we have A, 2B, solid, 2A, plus B 2 minus I C E. That's a solid, so we just leave it out. Yes? This is 0 and 0. This is plus 2x. This is x, and this is 2x. So it's up to you. If you want to show it this way, that's fine. Or you can show it that way. I know which one I like because it's shorter, but if you're like, I love rice, rice is good, it's delicious, tasty, tasty, then you can show the rice table if you want to. Okay? So basically those steps are listed out here. We're going to write the let statement. We're going to write the C. Underneath the C, we write the x's in correct proportion to the coefficients. Okay, and that's just what we did above. We've got x, 2x, and x. Or you can use the rice table. And then, guess what you need? After the C, you need a KSP, because you're finding KSP, right? Or you're given KSP. So you write your KSP expression, and then you plug in the value either from the question or from the data booklet. And then you solve for x. And don't forget that when you square your a, it has to be in brackets. You have to square both the 2 and the x. Sometimes people forget and they just write, we do not want 2x squared, like that, because the 2 needs to be squared as well as the x. Okay? So we will end up with then 4, since we're squaring the 2, and then x squared times x, which is x cubed, 4x cubed. Look at us doing math.
I know.
Right? No worries. What's up? Oh, yeah, for sure. No worries. Okay, we do our math, and we end up with x is equal to 0.021. And then we go back and we say, what were we asked for? We were asked for the solubility. So if x is 0.21, and look at us writing a let statement up here. Oh, look at that. Let x be the molar solubility of A2B. I know, right? No, in my math, I can do basic algebra. That's, Okay, so now we have that, and so the solubility of A2B is 0.021 molar, and that's our answer. Is that straightforward enough? Yeah, right? Not too hard. Okay, so why don't you try this one here. The molar solubility of AgI. Yeah, not that kind of problem. Did you guys get 9.2 times 10 to the negative 9? Yeah. Hooray! That means I didn't mess up. Now, these kind of questions can show up in written response, and so in written response you should have, this thing here for 0.5 marks. You should have this thing here for 0.5. You should have this thing here for 0.5, this thing here for 0.5, and then maybe 1 mark for all of this. So that would be like a 3-mark question, okay? But if this is multiple choice, could you speed this up? You sure could, because you know that this is a 1-to-1 salt, yes? We have a 1-to-1 ion concentration, yes? And we know that for a 1-to-1 salt, so that means like AB, just 1-to-1. KSP is equal to what? X squared, right? Because it's going to be A times B, and A is equal to B. Yes? And so for multiple choice, and this is where X is the solubility of AB. In other words, the concentration of AB saturated. Yes? And what if we have a 1-to-2 salt? This is like the first one we did. So for example, A2B or AB2. KSP is going to equal let's go back and look. Anytime you have an AB salt, you're always going to have a 2x, yes? And an x. What are you going to do with that 2x? The 2x is going to get squared, and the x is not going to get squared, yes? So you'll always have 2x all squared times x, and so that's always going to give you 4x cubed. Good Lord, stop. Yes? So, should you choose to memorize x squared and 4x cubed, you can use those for multiple choice. Don't just do that on written response, though. In the written response, show everything. Yes? So this here is for written response. And this one here, these are for multiple choice. And again, this is where X is the, I guess I should say molar solubility of AB. And really, those are your two most common types. I wouldn't bother memorizing anything more than that. You will unlikely come across it, and it's really easy to figure out even if you do, so yeah. So like I said, for multiple choice, if you just want to memorize those so you can just like quickly chuck things into your formula and be done, then you are good to go. All right. Calculate the solubility of FeOH3 in grams per liter. Off you go. Give that a try. So this is no longer molar solubility, but solubility can be any quantity per volume. Now, don't do like I usually do and go, oh, 3 cubed is 9, because it's not. I do that all the time, and it's so irritating. Yes. Oh, it's x to the 4th, isn't it? Yep, you're right. Where did I get the 2.6? It's in the data booklet. Data booklet, page 5. I did not leave myself enough room for this, did I? Oh well, that's okay. I'll just write smaller. Did you guys get x equals 9.906? Everyone okay with how to take a 4th root on your calculator? If you're not, call me over. I can help you with that. Okay. Did you get 1.1 times 10 to the negative 8?
Yes.
Yay! That means I didn't do it wrong. Hooray! Okay, so you should have your make sure, check through and see if you have everything. Do you have your let statement? And when you're talking about the let statement, you should say the molar solubility, just because in this case we are going to have to later find the grams per liter solubility. Did you write the C? Did you show your X's underneath the formula? Did you write your KSP expression, or did you just go chucking in X's without writing it? Did you plug everything in? And then did you solve for X? And then did you get your molar mass right and convert to that? And there you go. So that would be out of like 1, 2, 3. This would probably be out of 4. Okay. So shortcut for multiple choice. If you want to, like I said, you can know that KSP is equal to x squared. We've got 4x cubed, and should you so desire, if you have an A3b, you can use 27x to the 4th, but I don't think anybody's going to, it's not that useful. You can always figure that out by just using KSP and sticking your x's in there. Okay, there's some exercises. We're not going to do those right now. We're going to go to maximum and minimum problems. So this is a situation where we're adding one solution to another. And this is on page 69. When adding one salt to a solution of a different salt, and often we'll be adding like a solid in, which means we don't have a volume change. And before we were looking at, does a precipitate form if I add this much? Here we're looking at what is the maximum I can add without a precipitate forming, okay? Or what is the minimum I have to add in order for a precipitate to form, okay? And when we're looking at that little knife's edge where we're just at the point where a precipitate is just barely not forming, like we've got the maximum without one forming, and then we've got, a precipitate forms. That point right there is your KSP. So when ion concentrations are equal, that's when you've hit the maximum concentration of ions you can have without a precipitate forming. When you go anything beyond that, now you've got a value bigger than KSP, and you will get a precipitate forming. Okay? So we're looking for a situation where the ion concentrations are equal to KSP. Now, if this is when we mix two salts together, therefore, what type of a problem is this? Mix and match, yeah. And look, Mr. Colger says the same thing as I do. Their concentrations will not be in the simple ratio of coefficients in the equilibrium equation. Oh, look, in other words, they're mix and match problems. Given the concentration of one ion, what is the maximum concentration of another ion that can exist without forming a precipitate? So this is type A, where you're asked what is the maximum concentration without a precipitate. Given the concentration of one ion, what is the minimum concentration of another ion needed to start forming a precipitate? So that's type B, but they're solved the same way. So we are right on the edge of forming a precipitate. So we're going to use the KSP expression I'm making this up. I don't know if this is really what goes here. And the 1, or maybe I should say KSP value. KSP value. And the 1 given ion concentration to calculate the other ion concentration. So you'll have a KSP value. You'll have one of the concentrations of the ions, and you'll have a question that has 3 variables and you're given 2 of them. Is that easy to solve? Yeah. So long as you recognize this type of problem and you don't try and make them proportional to the coefficients, this is super easy. Okay? It's just a matter of saying, I know this type of problem. So here we have a large beaker, and it contains 2 liters of 0.1 molar copper nitrate. 2 liters of 0.1 molar copper nitrate. Who do you think is the ion of interest there? Is it the copper or the nitrate? Copper. Okay. And we want to know what mass of solid KiO3 would need to be added to this solution to just start precipitation. Let's assume that the addition of the solid KiO3 does not significantly change the volume. Yeah, so we're not adding a solution, there's no dilution, there's no big change in volume, so you can just say, we started with 2 liters, we finished with still 2 liters, okay? So we're adding Ki to water, and it's going to dissociate, because all alkali salts are soluble. What does it dissociate into? K plus and IO3 minus. Excellent. There's our salt. Okay, so we have, and we also have copper nitrate will also dissociate because all nitrate salts are soluble. So we have 2 liters of 0.1 molar Cu2 plus 2 NO3 minus, but we don't really care about the nitrate because the nitrate is a spectator. So we just ignore them. We're like, I don't care. Potassium nitrate, you might as well not be there. Okay, so here we have our KiO3, or actually just our IO3 minus because we don't care about the other thing, IO3 minus. And down here we have copper 2 plus because we don't care about the nitrate. Does molarity depend upon volume? Does the molarity of the copper 2 plus change if we change the volume?
Yes.
Oh, I'm asking the wrong question. Pretend I said nothing. Can you do that? Can you pretend I said nothing? Okay, awesome. That's fantastic. Okay, because I was thinking something different and the question came out wrong and it... Okay, so now we need to know, now we've got some iodate and we've got some copper, and we need 2 iodates for every 1 copper. So once the concentration of iodate is high enough, the ions will move together and the precipitate copper-2 iodate will form. Since we know the precipitate is copper-2 iodate, CuIO3, we can rephrase the question. What mass of solid KiO3 would need to be added to this solution to just start precipitation of Cu2+? Or I guess I could say CuIO3 too. CuIO3 2. So basically, you're always going to have to identify the precipitate. Anytime you have a mix and match type problem, you're always going to have to identify the precipitate. So when we did will a precipitate form, you had to identify the precipitate because that was a mix and match type problem. Here again, you're mixing 2 compounds. You have to identify the precipitate, okay? Identify the solid or the precipitate. So anytime you have mix and match, you got to do that. So step 1, guess what we're going to write? The C. Okay, this right here, that is the solubility equilibrium equation. Guess what else we're going to write? KSP. And then our unknown is IO3, right? Because that's like, we're like, what mass of IO3? Yes? But it's KIO3, but we're ignoring the K for now. We'll come back to the K later when we're worried about the mass. Yes? For now, we're just worried about the IO3. So we're going to use the KSP expression to find IO3 concentration. From there, you can find moles of IO3. From there, you can find moles of KIO3. And from there, you can find grams of KIO3. Okay? So basically, you're doing KSP stuff up to step 3. And then after that, it's just, moles and stoichiometry. Yes? Okay, so let's try this. Let's write our solubility equilibrium equation. Cu2 plus 2 IO3 minus aqueous. KSP is equal to concentration of Cu2 plus times concentration of IO3 minus squared. So IO3, I don't know why I haven't squared this. This should be squared here. IO3 minus squared is equal to KSP over concentration of copper and so now we're going to substitute in the known values, and KSP from page 5 data booklet, you go look that up. Copper 6.9 times 10 to the minus 8. 6.9 times 10 to the minus 8 divided by, and we have to go back and look, what was our concentration of copper? It was 0.010 molar. So we now have 6.9 times 10 to the minus 6. Sorry, this should be squared. And then we have 6.9 times 10 to the negative 6, right? But then we're going to take the square root of that, yes? Which is equal to 2.6 times 10 to the negative 3. Okay, let's see. 6.9 times 10 to the negative 6. Whoops. 6.9. No. It's because we divided by 0.01. So we get a negative 6. Yeah? Okay, so 6.9 e negative 6 square root. And I'm going to give some more digits here because I don't want to use a rounded value. So that's 6.627 times 10 to the negative 3. Because I'm going to need to use this value here, and this is in molarity, because that is our concentration of iO3. So then our moles of iO3, we have molarity. Do we have the volume? Yes, what is the volume? The volume is 2 liters. Is it 2.00 liters? No, just 2.0. Okay. So we have 2.0 liters times 2.627. Moles per liter. Whoops, times 10 to the negative 3 equals 5.254 times 10 to the negative 3 moles of KiO3. Well, you could do the calculation here with the mole ratio, or you could just say moles of KiO3 is equal to moles of iO3 minus, because it's a one-to-one, like you don't have to do any fancy calculation, right? Which is 5.254 times 10 to the negative 3 moles. Oops, I forgot to write my units there, moles and moles. And then we have 5.254 times 10 to the minus 3. This is KiO3. Moles, KiO3, times 39.9 plus 126.9 equals, oh, it's 39.1. Oopsie. 39.1 plus 16.3 plus 126.9 equals 214. Did you guys get 214 for the molar mass? Yes? Hooray. And then we get, as our final answer, 5.254 0.25 times 10 to the minus 3. What? What have I done? No.
You're multiplying this, right?
I forgot to, I forgot to actually multiply it. I forgot to press equals. Okay, so we got 1.124, 1.124 grams. And so we would round that to sig figs, which would become 1.1 gram. Is good? Okay. Cool, cool. So here is a thought about the maximum and minimum thing, and this is sort of visualizing that knife's edge between precipitate and no precipitate. When we have our Q value, so along this axis we have Q, right? And here we have KSP. I feel like these arrows heads are on the wrong place. Okay, get rid of that and put the arrowhead over here. There we go, that's better. No precipitate forms, and we're going to get rid of this arrowhead here. And we're going to add the arrowhead here. So if we go over the KSP, if Q is bigger than KSP, the solution is saturated and it precipitate forms. If Q is less than KSP, the solution is unsaturated and no precipitate forms. But when Q is exactly equal to KSP, the solution is just barely saturated, but no precipitate forms. So if you're looking for the minimum amount, or sorry, for the maximum amount you can add with no precipitate forming, you would just say that's my number. Okay? Now, if you want to start a precipitate forming, it's going to be the same concentration of ion B, or close enough, because technically you only have to add one extra ion in order to actually start the precipitation, because the maximum and minimum are the same essentially. So identify the precipitate because it's mix and match. And you'll recognize these problems because they say maximum, they say minimum. You're going to write the C. You write the C, write the KSP, plug in the KSP value. It'll either be given in the question. You're going to plug in one of the ion concentration, again, given in the question. And then you solve for the other ion concentration, and that is it. And then if the question wants you to solve for something else like mass or whatever, then you can do that. Okay, you might find moles, you might find grams, etc., etc. Let's try this one. It doesn't matter. There's two pathways you can take. You can take the concentration of sulfate and say that's going to be the same as the concentration of Na2SO4 because they're 1-to-1. And then you can find your moles of Na2SO4. So you can start by going from sulfate concentration to sodium sulfate concentration, or you can start by going from sulfate to moles of sulfate and then do the switch to your other compound once you're in moles. It doesn't matter. Either way is perfectly good. Okay? Any preference for which one I show up here? Nobody cares? Okay. I'm going to do the first one just for funsies. Times 2 is 32.1 plus 4 times 16 Did you guys get 5.1 times 10 to the negative 5? Yeah. Hooray, yes. Yeah. Yeah.
How would you do this question differently without the minimum?
Okay, so if I was asked for the minimum, I would say any amount greater than, I would put in my final answer, if asked for the minimum.
So basically you just have to answer it differently.
Yeah, ask for the minimum instead, minimum to start a precipitate. You would just say greater than. Greater than. Yeah, 5.1 times 10 to the negative 5 grams.
So for this, if it was asked for maximum,
Yeah, if I said maximum, so this would be the maximum without a precipitate. So that's fully saturated, but no precipitate. If asked for minimum, I would just say greater than 5.1 times 10 to the negative 5. Yeah?
So it's basically just asking for the most.
Yeah. So if for minimum, just add the two words greater than, and you're done. Okay? Otherwise, it's exactly the same question. Yeah? Are any of these problems difficult? Not really. The only thing that becomes difficult is when we sort of throw them all in one, and then you're like, oh, what type am I doing here? Okay? So that's why I've been so much think about it. Is it mix and match? Is it dump and stir? How do we do this? This is this type, this is that type. Okay? And I've got this whole little section about sorting them out. Yes? So, because that's really the only, other than that, the math is fairly straightforward. I think that's a good place to leave it today because we've only got 4 minutes left. You have a quiz tomorrow. Yes? On 3.2. I know you're studying for that, but can I get you to do one of each of these types of problems as well? Like, why not? So we'll do number 1 on page 75. And we will do number 1 on page 68. The quiz tomorrow will be short. Like, it's not going to be a long quiz. Because, like, what is there really for me to ask? Like, does this increase the solubility or decrease the solubility? In which is it the most soluble? In which is it the least soluble? How do the rates of dissolving and recrystallization compare in a saturated solution? How do they compare in an unsaturated? Like, there's not a lot I can ask you. Yes? So it will be short.
You just have to know that, right?
The meaning is that you take two solutions, you mix them, two of the ions match together to form a precipitate. Dump and stir, you take the low solubility compound, single compound, dump it in the water, stir it until you get no more will dissolve.
Oh, so one is just one substance, the other is just two.
One substance for dump and stir, two substances for mix and match, yes.
For dump and stir, you're just seeing how much it can dissolve, right?
Yep.
You just keep going until...
Yeah. Well, if you're asked what is the precipitation reaction, then you write the precipitation reaction. But if you're doing what's the minimum required to precipitate, you're going to still use your solubility. If you're using the Q, you're using KSP, so you need the solubility equilibrium equation. Because KSP is based on the C. Right? Where do we get that equation from? It comes from the fact that the ions are on the right. All of them you're going to need to see. Okay? Except for titration. Titration is going to be precipitation because you're not worried about the equilibrium. All the calculations will involve the C. Yes. Except titration. Yeah. Well, we did last year. So we'll review it this year. Yeah. In maybe next class? Yeah, next class we're going to be reviewing titration.
Okay.
Next week. Because I need to give you a quick math, right?
Yeah.
And then you get back to you.
Yeah. And then we study.
Yeah. So we'll start on your tie. I'm guessing Thursday, right? Yeah.
Because we're like halfway
Maybe Wednesday then. Yeah, you gotta get that. Yeah. I'll figure it out.
halfway through almost done.
Yeah, we're almost done. And quite frankly, after titration, it's just sorting them out. Right? We only have titration left. Right? There's 5 different types of problems. We've now learned 4 of them. And then titration is the 5th. And you kind of already know that, sort of. Bye. Bye. See you. Hey, where'd I put my sweater? 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 Maybe it's in the prep room. Okay, I will go look in the prep room.